Okay, I wanted to go over a couple things from our bonding unit, namely, how do we look at the structures of the Lewis structures to tell the shape or the molecular geometry, if the overall molecule is polar or nonpolar, and the hybridization. So the model for molecular geometry, right, it's all dictated around the central atom. So that's really what I focus on, is what's going on around that central atom. And then to tell if a molecule is polar or nonpolar, again, we look at the central atom. So the most simplified version of that is that the molecule will be nonpolar if all of the things around the center atom are the same. Okay, so I keep using the word things because around the center atom you may have bonds to atoms and you may have just electron pairs. So all of those count as a thing around the center atom. So if those are all the same, then we're going to be nonpolar. There are a couple exceptions, but that's a general rule we could go by. So I categorized all of these molecules, again, by the number of things around the center atom. Okay, so for example here, right, our center atom is shown by X, and we have 2 things around the center atom. Here again, our center is X. Now we have 3 things around the center atom. And again here, our center is X, and we also have 3 things, 1, 2 atoms, and 1 pair. So 1, 2, 3. So that's what I'm talking about by things around the center atom. So let's look at specifics. So if we have 2 things around the center atom, like this example down here, okay, center, and I have 1, 2 only, with no electron pairs, that is going to be a linear shape. Okay, and the only possible option here is that it has no electron pairs, because if you imagine if that was electron pairs, again, we just have 2 atoms. So any way to connect 2 things is just a line. So that would be linear. Okay. And our angle is going to be 180 degrees since they're linear. And the hybridization, we have 2 things around the center atom. So I need 2 orbitals for those 2 things. So S is 1, P makes 2. Okay, that's how I think about the hybridization. Let's go on to if we had 3. So if there's 3 things around, we have the option of them all being atoms, so there's no electron pairs, like this example down here, okay? And that shape is trigonal planar, meaning it's flat in a plane, and it just makes a triangle. So all of our angles then here, these angles are all 120 degrees. And our hybridization, we needed 3 things, right? So I need 3 orbitals, 1 s, and now 2 p's. So 1 plus 2, that gives us 3. The next option is if we have 3 things, so 1, 2, 3 things, it just so happens that one of those things is an electron pair. And the electron pairs then change the shape because you can't see them. So if you imagine you can't see that blue part, all you would see is this. And so that shape is called bent. And the angles are a little bit less than 120 degrees because these electron pairs are taking up more space. The name of this is valence shell electron pair repulsion, right? So it's all about how are these electron pairs repelling things to maximize their space. And when we have these free electrons on their own, they repel these atoms down. And so it makes this angle a little bit less than 120 because this needs some more space. So that's why we say the angle is less than 120 degrees. And again, since we have 3 things, 3 orbitals. So all the hybridization when we have 3 things around the center atom are going to be the same. So some specific examples here for a linear molecule might be like CO2, where you'd have C in the middle and 2 oxygens on the outside. Or you could have HCN, where we would have hydrogen, carbon, and then nitrogen. So let's look at what that means for polar versus nonpolar. So remember I said that it would be nonpolar if all the things around the center atom are the same. So in the case of, let's see if I can do this, CO2, right? And these are actually double bonds if you draw the structure, but it doesn't matter for us right now because we're counting double bonds, single bonds, those all just count as one thing. So carbon in the middle, I see 1, 2 things around it. Are both of those things the same? Yes, they're both oxygens. So that would make CO2 nonpolar. Now our other example where we have H, C, and then N, let's look at this. And again, this is technically a triple bond. So let's look at our center atom and the things that I have around it. I have 1, 2 things. Are they both the same? No. One's a hydrogen and one's a nitrogen. So that would make this molecule polar, right? And then whereas the CO2 was nonpolar. Okay, so hopefully that's making sense. If all your things are the same, you're going to be nonpolar. So let's look at an example like this with the 3. BF3. Okay, if you can imagine, B would be in the middle, and we'd have our 3 fluorines on the outside. So around our center atom, there are 3 things. Are they all the same? Yes, they're all fluorines. So that would make BF3 nonpolar. What about an example like this? CH2O. Well, C would be in the middle. We would have HHO. It has 3 things all around it. Are they all the same? No. 2 are H's and 1's an oxygen. So that makes this molecule polar. Okay? And then this other example, a common example, actually this is the wrong kind because bent would have 2 electron pairs on the oxygen. So ignore my example for right now. But if you had something where we have a center atom and 2 things are atoms and 1 thing is an electron pair, we have 3 total things around the center. Are they all the same? No. 2 are atoms and 1's an electron pair. So anything that's going to be this bent is going to be polar no matter what, because all 3 of those things are not going to be the same. Okay, so that's what I'm meaning by this. It's nonpolar if all the things around your center atom are the same. So they would have to be the same exact atom for that to be true. Okay, so the next thing, moving on, is if we had 4 things around the center atom. Okay, if you have 4 things and none of them are electron pairs, you would have this kind of configuration. We can see all the atoms, and that's a tetrahedral shape. So for that, our bond angles come out to be 109.5. So remember, this isn't flat. It's a 3D shape. So that's why it's not like 90 degrees, because it's not flat. Parts of these are coming out at you and going back. That's why in this drawing they're a little bit angled to try and depict that. Okay. And again, for the hybridization, if we need 4 things, I now need 4 orbitals. So 1s, 3 p's. That would give us 4. Okay. Again, we can go through polar, nonpolar. If we have an example like CH4, all the things around it are going to be H's with the carbon in the middle. Are all the things around the carbon the same? Yes. So that would be nonpolar. If instead you have a molecule like this, CH2Cl, 2. Okay, we can imagine you have carbon in the middle, and then 2 of those are going to be H's, and 2 of those are going to be chlorines. Are all 4 things around the center atom the same? No. 2 are hydrogens, 2 are chlorines. So this one would be polar. Okay, those dipoles are not all going to cancel out. So that one is polar. Okay. Our next option here is if we have 4 things around, but one of them are electron pairs, right? So here I see the X, and I have 1, 2, 3, 4 things around my center atom. So if 1 is an electron pair, again, we can't see it. And so what that looks like is trigonal pyramidal. And so basically that's like if you imagine these things are a triangle base going up to that kind of makes your pyramid. Sorry for the bad drawing. And an example of that is NH3, where you would see that structure. So again, is this polar nonpolar? Well, it has 4 things around the center. Are all of them the same? No. 3 are going to be bonds and 1's going to be electron pairs. So anything with this shape is going to be polar. Okay? And then our bond angle, same reasoning as before. These electron pairs repel these other atoms away more. These free electron pairs need more space. So it's going to squish in these other angles, and they're going to be slightly less than 109.5. And our hybridization then is the same. Our last option for 4, we have 4 things around the center atom, but now 2 are electron pairs. And so this is actually a good example, H2S or H2O, same thing, of a bent molecule. So since we can't see those 2, all we see is bent. And let's talk about the angle. Now we not only have 1 electron pair that's floating around there, we have 2. Those are going to take up even more space. So what commonly you see is less than 109.5. I think this angle actually comes out to be like 107, and this one comes out to be 104. And again, let's look at polar, nonpolar. 4 things around the center atom. Are they all the same? No. 2 are electron pairs, 2 are atoms. So this is always going to be a polar type of molecule. Okay, next up is if we have 5 things around the center atom. So here are our shape configurations. Okay, with 5 things around, and none of them are electron pairs, we'd have this top looking thing. And this is called trigonal bipyramidal. So if you could bear with me and kind of imagine, these ones make a triangle base. And then it's bipyramidal, meaning there's 2 pyramids. So up to this one on top, that's 1 pyramid. And to that one on the bottom, that is your second pyramid. So you have 1 pyramid on top, 1 pyramid on the bottom. Kind of looks like a diamond or something like that. But we call that trigonal because it's a triangle base. Bipyramidal, meaning there's 2 pyramids. So we have 2 different angles going on. We have the triangle base. Those are all at 120. And then you have this angle coming down from the top. Those are 90 degrees. So that's why for these you see 2 angles. And then our hybridization for all of these with 5 things around, we need 5 orbitals. So 1s plus 3 p's, that makes 4. And we need 1 more, so now we have to move into the d. So total, that makes 5. And then since we need our d orbital, we can also tell that these are going to be things with the expanded octet, right? They have more than 4 bonds around them. And so our hybridization also gives us a clue that these are going to be molecules where the center atom that has an expanded octet, meaning it has more than 8 electrons around it, they're going to be in energy level 3 or above because they need to be able to have that D available. So common things I've seen is like phosphorus can have an expanded octet, sulfur. Often the AP exam gives you examples with xenon, arsenic, things like that. Okay. So that was this first one, the trigonal bipyramidal. Let's move on to now if there's 5, but one of them is an electron pair. So if you actually turn this on its side, you can imagine it looks like a little seesaw. So you would have something like that. So that's why it's called seesaw. Okay. Now if we have 2 electron pairs of our 5, this makes a T. So it's called T-shape. Okay. Oh, and in our seesaw, this third part of our triangle base is the electron pair. And so that's why this says less than 120, because it's pushing those away and squishing this angle in to be a little bit less than 120. Okay, here when we have 2 electron pairs in our triangle base, we can't really see those anymore. So the only angles we have are these, and those are still going to be 90. Okay. And then if we have 3 electron pairs, that takes care of our kind of the triangle that we used to have. And now we're back to just a linear shape with a 180-degree angle. So let's go through polar, nonpolar. Up here, if all the atoms are all the same, then that's going to be nonpolar. If any one of these atoms is a different element, then it's going to be polar, because not everything's the same. Here, this structure would always be would always be polar, because around that center atom, even if all these elements were the same, we still have 4 things that are atoms and 1 electron pair. So there's no way all of that's going to be the same. Okay, so this is always a polar situation, and down here the same. This is always a polar situation. The exception is down here with our linear. So now all of these electron pairs in the triangle shape are actually kind of canceling each other out. And so what we really just have is our linear shape. So as long as these 2 elements are the same, you would be nonpolar, just like in the other linear situation. If these elements are not the same, then that's when you would be polar. Okay. So this one is a little exception to my rule. So I put a little star here. Because for the linear one, you would have to look at, even though they're not all the same, right? You'd have 3 electron pairs and 2 elements. If your elements are the same, now that is nonpolar. Okay, let's look at the last one that you have to commit to memory for the AP exam. And that is these 3 versions of having 6 things around the center atom. So the base geometry is called octahedral. Okay, you kind of have a square around the center in a plane, and then up and down 2 other elements. So all of these angles are 90 degrees. And again, if we think about our hybridization, we need 6 things around the center. So I now need 6 orbitals. 1s, 3 p's, that makes 4. So now my d's, I need 2 d's. So that makes 1, 2, 3, 4, 5, 6. So the hybridization for all of these with 6 things around is going to be the same. sp3d. Okay. So if now we replace one of those atoms with an electron pair, okay, we have a new shape. This is called square pyramidal or square pyramidal. So you imagine now this is a square base, and they're all pointing down to that point. So if I drew it right side up, you would see a pyramid like this with a square base. So that's why it's called square pyramidal. And then again, because we have this electron pair repulsion, this is going to be pressing on these and making the angles less than 90 degrees. If two of those are electron pairs, they're going to be the most spaced out they can be, so they're going to be in the up and down configuration, and all we're going to be left with is that square, the square base that used to be our pyramid. And so this is planar, all in the same plane, and 90 degrees again. So let's erase my little markings and talk about polar, nonpolar. Okay, so here again, if all the elements are the same, nonpolar. If any element is different, like all of these were Cls and one of them is a fluorine or something like that, all of a sudden now it's polar because they're not all the same. Okay, for this one, this is an automatic always polar because you're going to have 5 atoms plus 1 electron pair. No way for all of those to be the same. So this shape, the square pyramidal, is always polar. This one is another exception to our rule. So because these, again, are exactly opposites, which makes these all in the same plane, there's the opportunity for all of these in the square to cancel one another out. So if all of your elements around your center atom in this square planar geometry are the same, now it would be nonpolar, even though you have 4 atoms and 2 electron pairs, right? So it's not all the things are not the same, but because of how this geometry is, they would still cancel out and be nonpolar. If any of these elements is not the same element, then you're back to a polar situation. So here's our exception to this general rule of all the things being the same, it would be nonpolar. If you have the square planar, there's an opportunity for this to still be nonpolar even though you have 4 atoms and 2 electron pairs. Okay. So for AP Chemistry, what you need to commit to memory are all of these, right? If there's 2 things around the center, 3, 4, 5, and 6. So you just need to know these shapes, be able to figure out if your bond angles are compressed because of those electron pairs or not, and the hybridization. But again, most of the time they just ask you, what is the hybridization of, so for example, they'd say, what is the hybridization of X in this molecule? So you just have to look and say, okay, there's 1, 2, 3, 4, 5, 6 things around that X. So I need 6 orbitals. That would be sp3d2. Those are the types of questions I've seen most often on the AP exam. So here was kind of my version and way of thinking about the shapes and the angles and the hybridization. It's very similar to what was in your notes packet. This was the table in your notes packet. I just, instead of organizing it by the family name, I instead look at it through how many things are around the center. And that's really what I use as my, my driving force. So hopefully that helped. If you still have any questions, please let me know.